And let me okay. Okay. If you go to the periodic table, you see that for each of the element, we have the atomic mass units listed below this as below that specific element. For instance, in this case for hydrogen, you see 1.008. Basically, in our calculation, we consider that 1.01. Or like for oxygen here, we have the number 15.99. And then these numbers in different textbooks can be different. So in your textbook, specifically 16.00. But the rationale remains, and any of these numbers you use is valid. But for the sake of our purposes, you just use the periodic table in your textbook. But the numbers is fairly similar, and it can be used. So this is how you get these atomic mass units for specific elements. And you use these to calculate the formula mass for each compound of interest. Any questions about this? Okay. So if I can. Okay, so in order to calculate the formula mass, first we write down the number of atoms in the first element. So in the case of aluminum, how many aluminum do we have? 2, exactly. And then we go to the back of the book that I showed you, and then we see that, if we go, we see aluminum has the atomic mass unit of 26.98. Plus, we go to the second element. How many oxygen do we have? 3. Exactly. Multiply by, we go again to the back of the book or periodic table, and then we see that for the oxygen we have 16. And then after doing the math, we will have 101.96 atomic mass unit. Is this clear how we do this? Okay. So, as another example. Yes?
Won't we use the prefix tri before oxide because we have 3 oxygen?
What is the question again?
Like for naming the aluminium, won't we use the prefix tri before oxide? Like as we have 3 oxygens.
So that is for the elements that we, the number of charge is not fixed, but for aluminum is always 3, right?
Naming, will we use the tri prefix on like trioxide, or will we just try to use?
So you mean like the Roman letters, right?
No, the prefix with the second element.
So what do you say we should use?
What would be aluminium trioxide?
So that is for naming molecular compounds. This is ionic, right? So for instance, we say carbon dioxide because carbon dioxide is a molecular, but this is an ionic compound, right? Okay. So to give you another example, for instance, we have SF6. First of all, what type of compound this is? Exactly. So How would you name this one? Yeah. Say, oops. Sulfur. So, right. So to calculate formula mass, so how many sulfur atoms do we have here? Exactly. We have 1 multiplied by, again, if you go to your periodic table, you will be having something like this. And then if you go for fluorine, you're having something like this. So we have 1 sulfur plus how many fluorine? Exactly. And when you do the math, it was 146.06 AMU. Because we love molecular compounds, I give another example. As I said, it's molecular. How would you name this one? Anyone? Exactly. Thank you. Tetraoxide. So to calculate the formula mass, again, we say how many nitrogen atoms do we have? 2. Multiply, and then again you go to your periodic table, you have nitrogen, oxygen. Nitrogen is 14.01, oxygen is 16.00. So 2 of nitrogen plus how many oxygen? Exactly. 4 multiplied by 16. And then when you do the math, it would be 92 atomic mass unit. Any questions about this?
Question.
Yes?
Why are we rounding before we're doing all that multiplication?
Why do we round when? You mean when I write it here, like 19 or...
Yeah.
These are like the numbers that are given in the book, so I just use it as such. But if there has like more digits, you're welcome to use that one too. The answer wouldn't differ much. Actually, the way that you say it would be more accurate a little, but for our purpose, you just use the number in your book.
Okay.
Or like in the exam, if I give you a periodic table to use, you just use that number. But you,
Just round up before we do the math?
no, I mean, for atomic mass unit of each element, you use that number as such. So if you go to your periodic table and this number is like 19.001, you use that one, If it's like this, you use that one. But you round at the end. After you do all the calculations, you can round that number then.
Okay, so then on sulfuric hexafluoride,
Uh-huh.
I didn't round based on the periodic table I have, and I got a different number.
So what number did you get?
146.65.
146?
Yeah, on sulfuric hexafluoride.
So what numbers did you use?
32.66 plus.
32.66?
Yeah. Okay, never mind. That's just me then.
Okay, I think that, yeah. Because the numbers would be different, but not much that, concerns us. Yeah. Yeah, I guess that would be a typo, whether in the book or, miscalculations. Okay, any other questions? Are we comfortable with these? Good. Okay, now now I'm going to start chapter 6, which is chemical composition. Okay, so your book gives so many examples of why chemical composition is important. So the first example that your book gives is the fact that all of us, consume sodium, but we don't eat usually sodium as such. Usually we eat it as a form of salt, right? Sodium chloride. So sodium is a really important substance, and it controls the body fluid and regulation, fluid regulations of the body. And in basically Food and Drug Administration, FDA says that the amount of sodium in body should be 2.4 gram per day, because if we have lots of sodium, we can have high blood pressure, and then it can cause stroke and heart disease and so on and so forth. But we have this number, but how do we know exactly? This corresponds to sodium, right? But we eat sodium chloride, right? So if we want to measure how much salt we should consume each day, we should know that how much sodium chloride we should have every day in order to meet this criteria. So for that matter, we should learn how to calculate chemical composition and how do we know how to relate, specific elements of a compound. The other example is that, if we are interested, in having iron, or some companies that they want to extract iron from iron ore, they should know exactly that when they have the specific ore, how much of it is specifically iron. Otherwise, they wouldn't know that, right? So it's really important to know how to calculate chemical composition. So if you have a specific amount of one element in a compound, you can calculate, the composition of that specific element, or vice versa. So this is a way that your book wants to persuade you that this topic is really important. And there are several other examples that I encourage you to study. So one example that your book gives is that imagine you want to buy nails. Usually, when some people or some companies, they want to buy nails, they don't buy it one by one, because sometimes they want hundreds or 200, 300. So what they do, instead of counting nails one by one, they sell it or buy it by their weight. So imagine, there is a customer and they bought 2.60 pound of nails. And imagine we have a scale here that is accurate, and we have some nails on it, and it's 2.60 nails. And then imagine we are given that a dozen nails weigh 0.150 pound. And now the customer wants to know how many nails did they buy. So in other words, imagine you bought, certain amount of nails, and we don't know exactly how many are they, because as we said, it's really hard to distinguish one by one. But still, they are interested to know that exactly how many are there. And your book uses this example to teach you of a really, really important chemistry concept. But first, let's go through this example together. And the rationale of solving this problem stands during the whole chapter. So what I always recommend you to do is that anytime that you are given a problem and you want to calculate something, try to have words in numbers and then see what do you have, what are you given, and what do you want to calculate. So we are given 2.60 pound nails, and we are given that dozen nails weighs 0.150 pound, and we know dozen equals to 12 nails. And now we want to know, oops, come back. Okay, now we want to know how many nails. Basically, we want to know number of nails. And what I always recommend you to do is that anything that you want to, let me just get rid of this. Okay. Anything that you want to find or, is missing, you say number of nails equals. So anything that you want to calculate, you write it down, and then you have a equal sign. And then anything that is given in your problem, you write it in the right of the equation. So here we have like 2.60 pound nails. This is given. So we should write a conversion factor that when we simplify it, we would be having the number of nails. So here, if I write it as such, this and this cross out, and here, how can I relate the pounds to the nails? So here I have pound, and here I have dozen nails, right? Which dozen nails equals 12 nails. Basically, I can say that 12 nails weighs 0.150 pound. So here I can relate pound to number of nails. So basically 0.150 and equals to 12 nails. Any question about how I wrote this? So basically anything that you want to calculate, you write here, and anything that is given, you write here. And in order to you find what you want to find, you write a conversion factor, and you write it somehow that you can cancel out the term that is given, and then you find what you want to find. And then when you do the math, you would be having like 208 nails. So again, you were given, you went to a hardware store, you wanted to buy some nails, right? You were given, you were told that this is a specific type of nail, and it was like medium sized, imagine. You were told that, 12 of them, a dozen of them weighs like this much, right? And then, randomly you bought some nails, this much of nails, and then you walked out of the store. Now you want to know how many did you buy, right? So you know the weight of the dozen, how much it is, and depending on how much, the weight of the nails that you bought were, you can calculate just with a simple conversion factor how many nails did you buy. Is that clear? It's just kind of like, you just write a conversion factor. So after like this example, your book introduces a very, very important concept. So in the same way that, you couldn't just like, buy nails, you cannot go to the store, say I want like 350 nails. It's not practical, So it's the same thing with the atoms and molecules and ions, you cannot count them one by one. Even if you wanted to do that, it's not practical. So there is a number named Avogadro's number, which equals 1 mole, that I'm going to explain right now, which is like 6.022 multiplied by 10 to the power of 23 atoms, molecules, ions, etc. And we call that Avogadro's number, which is named after the scientist Amadeo Avogadro, who lived from these years. So 1 mole of anything is basically 6.022 multiplied by 10 to the power of 23 of that thing. Basically, 1 mole of anything is 6.022 multiplied by 10 to the power of 23 unit of anything. So basically 1 mole of marble would be 6.022 multiplied by 10 to the power of 23 marbles, or like 1 mole of grain sands would be 6.022 multiplied by 10 to the power of 23 of grain sands. Or like, 1 mole of books would be 6.022 multiplied by 10 to the power of 23 books. Any questions about mole? And then, to give you a better understanding of mole, and then give you a better visual of it, your book tells you that if we have like 22 copper pennies, and considering that the pennies are made of copper, you have approximately 1 mole of copper. Or like if you have like 2 balloons of large helium balloons, it would be equivalent to 1 mole. Kind of like, helping you, have an understanding of how much a mole is. So you may wonder how we got this number. Is it like random? We just like agreed, or Avogadro rather agreed that, okay, this much, I just call it 1 mole. No, there is a specific way of why we define this number. So basically, I'm going to write this down. The specific numerical value of mole is defined as being equal to the number of atoms in exactly 12 grams of pure carbon 12. So if we have like 12 gram carbon 12, which is pure, it would be exactly 1 mole. So basically, in other words, we can write that if we have like 1 mole equals of 12 gram. So knowing, as we said, 1 mole is like 6.022 multiplied by 10 to the power of 23 of anything. So with the same rationale, we can convert between number of atoms and mole easily. And we have like 2 different conversion factors. One of them is like this. 1 mole is like 6.022 multiplied by 10 to the power of 23 atoms. The other one is like reverse. And then depending on the problem, what do we want to find, we use one of these 2 conversion factors. So with the same rationale that we had like the nails, and then having that dozen concept allowed us to convert between their weight and their number, this Avogadro number does the same thing. It's kind of like a dozen. But for the sake of atoms, we couldn't use 12. That was too small. But here, we can convert between like grams, basically between weight and number of atoms. And also we can convert between mole and number of atoms, as you can see here. So let's go through some examples to kind of like understand this concept better. So imagine we are given 3.5 mole of helium, and we are told to find number of helium atoms. So as I told you, the thing that you want to find, if you write it down on the left, and then the thing that you are given, you write on the right, 3.5 mole of helium. And then you should write a conversion factor so that you can find what you want to find, So here, if I write mole of helium, these 2 cross out, and then I can find number of helium atoms. And as I said, this is universal. 1 mole of anything is 6.022 multiplied by 10 to the power of 23. And then when you do the math, you'll find 2.1 multiplied by 10 to the power of 24 helium atoms. Any question about mole, or how do we write these conversion factors or calculate these things?
Can we do one more example of that?
Yes, of course. So imagine we are given, okay, I'm going to write the question too. A silver ring contains 1.1 multiplied by 10 to the power of 22 silver atoms. How many moles of silver are in the ring? So it is really useful, as I said, to have words in numbers so you know what you have and what you want to find. So we are given 1.1 multiplied by 10 to the power of 22 silver atoms. And we want to find moles of silver. So the thing that you want to find, you always write on the left, you say how many mole of silver or Ag equals the thing that you are given you have. 1.1 multiplied by 10 to the power of 22 Ag atoms. So here till now I just wrote whatever I was given in the problem statement. So I didn't solve the problem yet. I just wrote, but it's important to know how to write this so that you can find the answer easier. So here I write a conversion factor. So I want to find the mole. So here I should have like mole basically in the numerator so that I can find the mole. And then in the denominator, I will have like number of Ag atoms so that this one cancels with this one. And then I have mole of silver at the end, right? And then I told you 1 mole of anything, and then it's the same thing with the silver, is like 6.022 multiplied by 10 to the power of 23. And you should memorize this number by just saying it several times. I guess by now you memorize it. 6.022 multiplied by 10 to the power of 23. So first of all, remember that the number is big, so the power is 23. So and then the number is roughly 6, but exactly 6.022. So just memorize it, right? And then after that, you can just like do the math, and then you can cross this with this, and then this would be just 10 here instead of 10 to the power of 23. So in my time, we weren't allowed to have calculators, so we had to do this manually. But now you can have a simple calculator. So you just like put the numbers in the calculator, and then one of our professors were saying that you put it in the calculator and then you get it wrong. But hopefully you get it right. It would be mole of Ag. Any questions? Is it clear how we do this? Okay. So can anyone tell me what is 1 mole? Yeah, just shout the number. Okay, cool. I mean, I didn't understand it well, but I assume you said it right. So let's go through, now that we have like some time, let's go through some examples together. So when you see these in the exam, you won't be surprised. So can anyone tell me what type of compound this is? Yes. And can anyone name the compound? Yes. So we have lead, 4, if we can, chloride. And now we want to calculate formula mass of this. Okay. So how many Pb atoms do we have? Yes, 1 multiplied by. And then you go, again, I emphasize, you go to your periodic table. Here you find lead. And then after going there, you find that the atomic mass unit is 2O 7.2 plus. How many chlorine do we have? Yes. And then again, you go to your periodic table, and then here you see that bottom of chlorine, you have the number, the atomic mass unit. And then after doing the math, you will be having like 412 atomic mass unit. So this is a challenging one. I mean, not challenging, but compared to the other ones, a little more challenging, I guess. So first of all, what type of compound this is? Exactly. And then can you name this? Anyone? Yes, but you also should name because iron is one of the elements that can have multiple charges, so you should name how many charge it has, right? So it would be like, right? And then to calculate the formula mass, you say that, okay, how many Fe do we have? 1. And I'm just going to write this quickly. Imagine you go to the back of your book, you get the number. How many oxygen do we have? Exactly. And then you know the numbers for oxygen. How many hydrogen do we have? Exactly. And this is how you write this. So if you have like polyions or polycations, or basically, these two refers to each of the elements in the polyanion, right? And then after doing the math, it would be 89.87 AMU. So when you know how to do this, the rest is kind of like the same, You have the number of atoms multiplied by atomic mass unit plus, the second element and the third element and so on and so forth.